Pascal's principle, applications in solving problems. Welcome. In Pascal's principle, the change in pressure applied at one point of an enclosed, incompressible fluid is transmitted and diminished to every portion of the fluid and on the walls of the container. If we have a container of water which is sealed at the top, the pressure at a point P at a depth h is equal to the pressure naught P naught, which is at the top of the fluid, plus the liquid pressure. So P naught may be atmospheric pressure or the pressure exerted by the lid or the seal, something like that. But if we exert another force on the lid that increases the pressure of the liquid such that pressure at point P changes to P prime and P naught changes to P naught prime, then the expressions of pressure at point P and P naught will change as follows. So P naught will have the initial P naught prime plus a change in P naught, which we call delta P naught. Same case to point P. So the new pressure at point P will be P prime, which is P, the original P, and an additional delta P, the change in pressure. So according to Pascal's principle, the change in pressure, the delta P and delta P naught, is said to be the same. So let us see how this happens. But from figure 1b, we know that P naught, pressure at point P naught, P prime, sorry, the new P is equal to the pressure at the top P naught prime, which is significantly, we can say, the pressure due to the mass which has been added, the seal and the atmospheric pressure, then plus pressure exerted by the liquid, which is rho GH. So delta P from the equation 2a should be equal to P prime minus P. It's just a rearrangement. Then delta P should also be the same as, if we substitute the values of P prime and P, we have the values of P prime from equation 3 and the values of P from equation 1, then we get P prime naught plus rho GH minus P naught plus rho GH. Take note that if we open the second bracket, then rho GH and rho GH will cancel out and we will remain with delta P equals to P naught prime minus P prime. But what does this represent? It is essentially equation 2b. The right hand side, P naught prime minus P naught, can be equated to the second part, the right hand side of equation 2b. Then therefore we can say that delta P is the same as delta P naught. What does this mean? That the change in pressure at point P is the same as the change in pressure at point P naught. That is Pascal's principle. Now let us see how it can be applied in a hydraulic machine. Think about the hydraulic machine. How does it work? So a simple sketch here to illustrate hydraulic machine has the input piston and the output piston, and an incompressible liquid is trapped between the two pistons. If you look at the cross-section area of the pistons is not the same. There is the reason here. That pressure is applied at the input piston by exerting some force on it. Then by Pascal's principle, the pressure that has been applied at the input is transmitted undiminished or unchanged through the liquid to the output piston. But this same pressure generates a much larger force than the one applied or the one exerted at the input. What does this mean? How can we generate a larger force by applying a smaller force at the input, yet the same pressure is transmitted? So that's what we are going to get right now. Remember that pressure at point y2 is equal to P naught plus rho GH. Pressure at point y2, this point, is the same as pressure at the surface P naught, which is essentially pressure exerted by the input piston plus the atmospheric pressure, then plus the pressure exerted by this water column here, which is equal to rho GH. Now, if we apply some force, we exert some force at the input piston such that we lower the column or the level of water to P2, then the pressure will be transmitted to the output piston and the water level or the level of the liquid will rise. It is not a must to use water. The level of the liquid will rise in the output piston. So the input piston has a smaller cross-section area that generates high pressure from a small force. Then the output piston has a larger surface area that helps exert a large upward force that is greater than the applied force from the same pressure transmitted. So what do we mean? That here we have a smaller cross-section area as compared to this output area A out, which is larger, and that makes the difference. That if we apply a force here, then that force will be magnified in the output. So to achieve this, we are saying that the input piston moves a greater distance than the output. If you look at the input piston, it has moved from this point P0 to P2, which is represented by H2, while the output piston has moved from P0 to P1 as represented by H1. So we can say essentially that pressure at point P2 may be equal to pressure at point P1, which is the surface, plus rho GH. But at this point, the difference between point P1 and P2 in terms of distance is equal to the H2 plus H1. The H1 and the H2 here makes this distance, the total of this. So to get P2, we have to take into account P1 plus rho GH, which is rho G, then the sum of H1 and H2. But now, what is the change in pressure which has occurred from the point P0 for the input piston, from the point P0 to the point P2, and for the output piston from P0 to P1, or P1 to P0 to P1. So the change in pressure is the same as P2 minus P1, P0, which is the same as P0 minus P1, because the same pressure which has been exerted uh, in input piston must be taken into account, or must be the same change in pressure at output piston. So that means that delta P should be equal to rho g H2, or can we also say that delta P equals to rho g H1? So that will seem to be different, because delta P cannot be, H1 and H2 cannot be the same. Therefore, the values of change in pressure will be different. But let us see, is there a liquid in column H2? Currently there is no. Therefore, the change in pressure may be only accounted for by rho g H1, not rho g H2. But now, to get a better value for pressure, change in pressure, we have to consider the difference in the cross-section areas. So because we say that the cross-section area here is very small compared to cross-section area out there, so the change in pressure should be equal to the force exerted in the input piston divided by area of the input piston, which should be the same as force which is exerted on the output piston upwards, divided by the area of the output. Remember that pressure equals to force over area, and that by Pascal's principle, the pressure exerted in the input should be seen in the output. So from the same equation, we can make F out the subject of the formula, such that we have equation 5, which is F output, force at the output, equals to force at the input multiplied by the ratio of area at the output and the input. And this will give us a very good point here, that if area at the output is greater than area at the input, which is as in our case here, you can see that the area at the output is greater than area at the input, then the force at the output will have to be greater, because force at the input will have to be multiplied by a factor which is greater than 1. So if output area is larger than input area, then force generated at the output must be greater than the force applied at the input. Then if we calculate the volume is equal to cross-section area multiplied by height, or multiplied by the length, because this is something like a cylinder, and therefore the area, remember from Pascal's principle, the transfer of pressure is proportional to the transfer of mass. Therefore, the volume which is displaced at the input is added to the output. How will this assist us? We have this equation 6, which is actually an equation for conservation of energy, or what we say that work done at the input piston is the same as, we are trying to show that work done at the input piston is the same as work done at the output piston. Work at the input piston should be equal to the force applied at the input multiplied by the distance moved by the liquid at the input, which is H2. But we have the values for F, force at the input, from equation 5, and we have the value, or the equation representing the H2 value from the volume calculation. And we can substitute them into the equation, and they give us the force at the output multiplied by the distance moved at the output, which is work done at the output. Then this means that work done at the input is equal to work done at the output. And this shows that this system obeys the law of conservation of energy. So even if the force generated is greater than the force exerted at the input, still energy is conserved. But now the force at the output from equation 6 can be rewritten in the form in terms of the force at the input and the heights, now not the area of cross sections. So it is equal to force at the input divided by multiplied by the ratio of H2 to H1. So if the claim that force output is greater than force input holds, then the distance moved by input piston have to be larger than the distance moved by output piston. And this explains why we need to rotate the axle of the hydraulic jack very many times to lift a heavy vehicle over a very small height. So what we mean here essentially is that for force output to be greater than force input, then the distance moved by the effort or the force exerted at the input has to be larger, the H2, than H1, which is the distance moved by the load, which is now maybe the vehicle. And again, the area at the output has to be larger than the area at the input. A solved example of Pascal's principle or the use of Pascal's principle in a hydraulic jack. So a hydraulic machine was used to lift a 2000 kilograms heavy vehicle by a height of 10 centimeters to change a wheel that had been punctured. So the driver applied a constant force on the input piston, which moved a distance of 20 meters. This is about 20 revolutions. Now determine the work done in lifting the vehicle 10 centimeters higher and the force applied at the input. Take acceleration due to gravity to be 10 newtons per kilograms. Please pause this video and attempt this question, and then you can see the solution later. Now, for the first question, the work output should be equal to force output multiplied by the distance moved by the load, that is the vehicle. So if the vehicle moved a distance of 10 centimeters, that is equal to 0.1 meters, and we have the mass of the vehicle, which is 2000 kilograms, we can calculate the force output or the force exerted by the vehicle to be 2000 multiplied by 10 to make 20,000 newtons, and then work done at the output or work done in lifting the vehicle has to be 20,000 multiplied by 0.1 meters to make 2000 joules or 2000 newtons meters. Then the force applied at the input is equal to, remember we said that energy has to be conserved, and therefore work done at the input should be equal to the work done at the output, which we have calculated to be 2000 joules. Therefore work at the input is equal to force at the input multiplied by the distance moved by the input piston, which is D1. But force at the input is equal to work done at the input divided by distance moved by the input piston, which is 20 meters. So the force applied at the input is equal to 100 newtons. I want you to compare the force applied at the input and see how it has been magnified from 100 newtons to 20,000 newtons, and one person has been able to lift a very heavy vehicle 2,000 kilograms over 10 centimeters. This is how smart or how efficient Pascal's principle can be. Thank you. I hope you enjoyed this video. Please like, subscribe, and share. And come back for more videos on physics and chemistry and science tips in general. Thank you.